Okay, consider this situation. Let's say there is a non-uniform rod. Conductivity of the first part, let it be 50 SI units. SI unit for conductivity is watt per meter per Kelvin. Okay, so let's say conductivity for the first part is 50 units. Length is 2 meters and area of cross section is some 20 centimeters square. Okay. Second part, let's say the conductivity is 100 watts per meter per Kelvin and length is 1 meter. And let's say its area of cross section is some 10 centimeters square. Okay. So you are given a connection of two different rods. Okay. So basically two different thermal conductors. Fine. Let this end be maintained at a temperature of some 100 degrees C. Let the other end be maintained at a temperature of, let's say, 0 degrees C. Okay. First question, find out the heat current. Second question, find out the junction temperature. Okay, you will assume steady state is established. Under that condition, calculate heat current and junction temperature. Solve this, all of you. Okay, there are two ways to proceed as we had discussed. Uh, you can assume the junction temperature is T and write an equation like heat current in this part is equal to heat current in this part, because as I said, steady state is established, so heat current should be same in every part. That is one way to solve, and with that you can get the junction temperature, and then using junction temperature you can tell the heat current also. Otherwise you can do it the other way. Treat them as thermal resistors. Okay, find out the resistance of this part and find out the resistance of this part, and then resistors are in series. You know the effective resistance, you know total temperature difference and the effective resistance. You can get the heat current by applying Ohm's law. After deriving heat current, you can find out the junction temperature. So whichever way you want, you can solve. Let us do it the resistance way. Okay, we'll find out heat current first. Okay, I got one answer as junction temperature as 33.33, means 100 by 3. Okay, and heat current is 3.33, means 10 by 3. Let's see. So we are going to treat them as thermal resistors. The formula for thermal resistance is L by Ka. Okay. In whichever part the conductivity and area of cross section are uniform, for that part you can use L by Ka. Okay. If K value changes, then you can't use L by Ka for the entire rod, I mean entire system. So first part, its length is its length is 2 meters, L, divided by conductivity is 50 and area of cross section is 20 centimeters square. So in meter square, it will be 20 into 10 power minus 4. Okay, I'm writing everything in SI units. So this becomes numerator 2 into 10 power 4 divided by 50 into 20, well, that is 10 power 3. So effectively 20. Okay, I'm not writing the unit, let it be. Or if you want, you can write the unit also. V is equal to IR. R will be V by I. In case of heat, it will be temperature difference divided by the heat current. Temperature difference will be in Kelvin. Heat current will be in watts. So you can write this as Kelvin per watts. Okay. So that's the thermal resistance of the first part. Similarly, thermal resistance of the second rod, if you see, length is 1 meter divided by conductivity is 100. And then area of cross section is 10 centimeter square. So 10 into 10 power minus 4. So denominator becomes 10 power minus 1. So effectively it is 10 Kelvin per watt. Okay. Now these two thermal resistors are connected in series. Therefore, the effective thermal resistance of this combination becomes R1 plus R2, 20 plus 10, 30 Kelvin per watt. Okay. Now we know the effective thermal resistance of this combination of rods, and we know the total temperature difference, 100 minus 0. Okay. Therefore, current V is equal to IR, I is equal to V by R. In case of heat current, I will be temperature difference divided by the effective thermal resistance. Temperature difference across the combination of rods is 100 divided by effective thermal resistance is 30 now, 10 by 3 watts. Okay. Now, once you know the heat current, finding out junction temperature is quite easy. You just write the equation for heat current in any one part. Okay, I'll take the left side part. And I'm going to write the equation for heat current towards right, like this, in this direction. Why does direction matter? Because in whichever direction you want to express the heat current, based on that direction, you will have to take the temperature difference, initial temperature minus final temperature. So if I'm writing heat current towards right, then I'll write 100 minus T. Okay. Now we got heat current as 10 by 3 watts. So 10 by 3 should be equal to, what is the conductivity of the first part of the first rod? 50. Okay. So K, area of cross section is 20 centimeters square, 20 into 10 power minus 4. Temperature difference is 100 minus 0. That is 100 itself. Sorry, not 100 minus 0. 100 minus junction temperature divided by length of the first part of the rod is, first rod is 2 meters. Okay. That's all. From here we should be able to get the junction temperature. You get 100 minus T is equal to, cancel 1 0, send 2 that side. 2 divided by, okay, 10 power minus 4 will go to that side and become 10 power plus 4. Divided by 5 into 20 is 100. So cancel 2 zeros. 100 minus T. Wait. Okay, divided by 3 is also there. 100 minus T is 200 by 3. So T becomes 100 minus 200 by 3. That is 100 by 3. Good. And this will be in degrees C. 33.33. Okay, so on, good. Both answers are correct. Others also, have you understood how to solve heat current as well as junction temperature when rods of different conductivities and areas of cross section are combined? Okay, next try this question. This is also based on junction temperature. Read the question carefully and solve. Fine. It is given that there are two rods, one made of copper and the other made of steel, same length and same cross-sectional area, but materials are different, copper, steel, so conductivities will definitely be different. They are joined together. The thermal conductivity of copper and steel are given to you. The free ends of copper and steel are held at 100 and 0. The temperature at the junction is nearly. Okay, so it's very similar to the previous question that we solved. But this time, the question is only asking you junction temperature. So there is no point calculating heat current. Okay. So just imagine two rods joined next to each other. Now, heat current in the first rod should be equal to heat current in the second rod. They are joined one after another. Okay. So you just need to write heat current through copper is equal to heat current through steel. Use the direct formula. Now, the free ends of copper and steel are held at 100 degrees C and 0 degrees C. So suppose from here to here is copper and then from here to here is steel. One end is at 100 degrees C, the other end is at 0 degrees C. Junction temperature is what we want. So temperature difference across copper will be 100 minus T and temperature difference across steel will be T minus 0. That's all. So directly write K of copper, area of cross section, delta T divided by L is equal to K of steel, area of cross section, delta T divided by L. That's all. They said areas and lengths were equal, so they'll get cancelled. So K1, conductivity of copper, which is given as 385. So 385 multiplied with 100 minus T is equal to conductivity of steel is given as 50 multiplied with T. Solving this equation, you can get the temperature. And because 100 and 0 are taken in degree Celsius, you'll get T also in degree Celsius only. Okay. Next, let us look at a slightly difficult situation. Just a moment, I'll draw the diagram. Okay. Suppose there is a thick spherical shell. Okay. Means it's a hollow sphere. It has a cavity inside, but the wall is not very thin. It has a significant thickness. And let's assume inner radius is small a and outer radius is small b. Right? So distance from the center to the inner surface is a, distance from center to outer surface is b. So there is significant thickness. And let's say the conductivity of this material is K given to you. Now, outside the sphere, let's say the temperature is T2. And inside the sphere, let's say the temperature is T1, assuming T1 more than T2 or T2 more than T1, doesn't matter. Okay, but they are unequal temperatures. Okay, so there is some material and temperature difference is also there. So definitely heat will pass, okay, from one side to the other. Let's assume T1 is more than T2. If you assume T1 is more than T2, heat will be flowing from inside to outside. Okay, let's say there is a hot object placed inside. Fine. Or let's say there is hot air inside and cool air outside. So there is a temperature difference across this shell. So heat is going to flow like this from inside to outside. What we have to find out is the rate of heat flow. Okay, when the temperatures are T1 and T2, assuming steady state, we will have to find out the rate of heat flow. Can you come up with ideas how to do this? I hope you can I hope you are able to visualize the situation properly. It's a spherical shell like a ball, okay, with significant thickness. We have to derive an expression for rate of heat flow. So how can this be done? Think about it for 1 or 2 minutes. See, what do we know about thermal conduction? Like if like it arises due to a temperature difference, there's a temperature difference. That's fine. And the formula we have is dq by dt, heat current. Okay, that is the rate of heat flow. Is Ka delta T divided by L. But this has its own conditions which need to be satisfied. Conductivity has to be same everywhere. Area of cross section should be same everywhere. You should know temperature difference and length. Okay. Now in this situation, we have visualized how heat is going to flow. Since T1 is more than T2, it is going to flow from inside the sphere to outside. But as heat flows, can one of you tell me, like, why were you not able to come up with any idea? What is the problem here? Or why can't we use this formula? Conductivity is given to you. Then what is the problem? So you need to visualize heat flow. Heat is flowing. Okay. Yeah, one of you unmuted. Do you want to share anything?
Sir, the object is three-dimensional.
Object is three-dimensional. Okay. Every object in real life is three-dimensional only. Like the rods that we considered before also, they had significant area of cross section. Okay. This was not negligible thickness. This is also three-dimensional. It's like a cylinder. Okay. But why is that a problem? Okay. See, if you consider a rod or a cylinder, let me quickly draw one here. Let's say this end is at one temperature, the other end is at another temperature. Heat flow will be taking place. Visualize heat flow. Heat flow will be from one side of the rod to the other side. Okay, assuming T1 is more than T2, this is the direction of heat flow. As heat flows this way, You now visualize the cross section through which the heat is flowing. Okay. Anywhere the area of cross section through which the heat is flowing, okay, since the rod is cylindrical, the area of cross section will be circular like this. And it will be the same everywhere. It's a rod of uniform area of cross section. So these are the areas of cross section through which heat is flowing. And that area of cross section is same everywhere. Now you visualize heat flowing in this case. Now this, as Sohan pointed out, it's a three-dimensional system. On screen, it looks like 2D. Okay, but you have to imagine it like a sphere. Now as heat flows out from inside to outside, you visualize the area of cross section. Okay, now closer to the inner surface. Okay, closer to the inner surface, the cross section through which heat passes is this. Okay, maybe I should draw slightly thicker. Okay, on screen it looks like a circle, but in 3D, this will be a sphere actually. The blue one that I'm drawing now is like sphere, is a sphere. Heat has to pass through that sphere. Then it will enter the next spherical layer, and so on. So this thick spherical shell that is given to you, the original system that is given to you have to imagine it as a collection of thin spheres. Okay, so heat will have to pass through this blue sphere first, then it will have to pass through another sphere, maybe somewhere here. So it will have to pass layer by layer like this, spherical layers. Okay. Okay, let it pass spherical layers. We know how to write the area of a sphere. So how is this a problem? The difficulty here is that as heat passes from layer to layer, the area of cross section that it has to pass through changes. So this is a case of variable area of cross section. Okay, you can visualize it better this way maybe. Consider this as one shell, this as another shell. So the given thick spherical shell is a combination of many thin shells like this. Okay, we can consider one more also. Okay, it's somewhat like this. As heat flows from inside to outside, okay, it will have to cross the spherical layers one by one. Fine. So as heat is flowing outwards, the cross-sectional area through which it passes is spherical, is in a spherical form, and that area will keep changing. Okay, as the heat is going from inside to outside, the first cross-sectional area that it comes across will be small. Next cross-sectional area that it comes across will be slightly larger, and so on. That way, the cross-sectional area will go on increasing. Okay, you can consider another system also, say like this. Suppose there is a solid cone, okay, a three-dimensional solid cone which has been cut out. Okay, like the tip has been cut. If you cut the tip of a cone, the remaining part is called frustum of the cone. You can imagine something like this. Let's say one end is maintained at temperature T1, the other end is maintained at temperature T2, T1 being more than T2. Then heat will flow from one end to the other end. Now, as heat flows through this cone, if you visualize the heat flow, it will be flowing like this from high temperature to low temperature. Now, as it flows like this, you visualize the area of cross section now. Okay. If you cut the cone like this, you will get circles only, but you will get circles of different areas. The area of cross section keeps varying as heat flows forward. Okay, first it will have to pass through small circles, then it will have to pass through bigger and bigger circles, and so on. Now, the same thing happens with sphere also. Okay, as heat flows from inside to outside, it has to pass through varying area of cross section. So that is the problem here. We can't directly apply the formula Ka delta T divided by L and get the heat current. Okay. So how to solve now? Whether it is that sphere question or this cone question. Now, the only thing you can do is apply this formula for the part for which area is uniform. So this can be applied only if area of cross section is uniform. Okay. Now consider this cone situation. As you move from left side to right side, the area of cross section will keep changing. But if you consider a very small distance, okay, like take a very small distance, something like dx. If you consider a very small distance through which heat is flowing, you can assume the area of cross section doesn't change much. Okay, you can assume for that small distance, the area of cross section is uniform. Next small distance, slightly bigger area of cross section. Next small distance, another bigger area of cross section, and so on. So, in a small distance for heat flow, you can assume the area of cross section is uniform. In that small distance, also, area of cross section changes slightly. That's fine, but we will ignore the change because it's very, very slight. So, that is how we are going to proceed. So, learn how to approach problems based on conduction. You need to visualize heat flow. Now, the same ideas will be used in electric current also in your 12th class chapter. Okay, you have to imagine the current flow, cross-sectional area and all. So, try to understand how to approach. So, first visualize heat flowing from high temperature to low temperature. That we have done. In case of cone, we have done. In case of sphere also, we have done. Heat flows from inside to outside. Okay. As it flows, visualize the cross-sectional areas. Cross-sectional area will be perpendicular to heat flow. For example, if it is a cylindrical rod like this, heat flow is along the x-axis, cross-sectional area will be in the yz plane. If you cut the cylinder like this, you get circles. So cross-sectional areas are circles. Similarly, in case of a sphere, since the heat flow is radially outward, you imagine a surface perpendicular to heat flow, the cross-sectional areas will be spherical layers. Okay, so heat has to pass through spherical layers one by one. If it is a cone like this, again cross-sectional areas will be circles. Heat has to pass through circles one by one. Okay, circular areas one by one. So as it is passing, since the area of cross-section is varying, for a small distance, you can assume area of cross-section to be uniform. Okay. So let us do that in case of this sphere itself. Just a moment. Okay. As heat flows radially outwards, okay. Radially outward means along the radius in the outward direction. Let's consider a spherical layer through which heat is passing. Okay, I'm showing that layer in blue. And that layer should have some thickness. Okay, many such layers having small, small thicknesses put together become the complete sphere, complete spherical shell, thick spherical shell. So let's say that layer that we are considering is somewhat like this. We can shade it also, but as I said, on screen in 2D, it looks like a circle. You have to imagine this in 3D, then you can imagine it as a thick spherical layer. Okay, small thickness it will have. So heat has to pass through many small layers like this. Okay. So what we are going to do is we are going to treat the given original system, which is that thick spherical shell, as a combination of many thin spherical shells like this. One I have highlighted in blue. Like that, you can imagine many. And heat has to pass through spherical shells one by one. Okay, spherical layers one by one. So from one spherical layer, like this blue one, to the next one, what is the difference? The area of cross section is different. Okay. So since heat has to pass through layers one by one, we will treat each layer as a thermal resistance, and it has to pass through layers one by one means it has to pass through the resistances one by one. So we'll assume they are placed in series. The resistances are placed in series. Okay. Same idea can be used in the case of this cone also. Fine. One layer we have highlighted in green, another layer you can highlight in blue. Cone problem we are not solving, but this is how you are going to solve if you ever want to solve. Okay, like this. So as heat flows from layer to layer, the layers are circles. In case of a cone, the cross-sectional area is a circle. So you'll have to give some thickness to that circle. So it's like a disk. So it has to pass through the disks one by one. So you can treat each disk as a thermal resistance. The resistances are placed next to each other. So it's like a series of resistances. Same thing in case of sphere also. Okay. So what we are going to do is we are going to find out the thermal resistance of this layer. Okay. And since it's a very thin layer, it will have a small thermal resistance. We'll have to call it dr. And many such thermal resistors are in series. Therefore, total thermal resistance will be the summation of all these drs. Okay, summation means integration. Integrate all the small thermal resistances, you will get the total thermal resistance of the given object. And once you know the total thermal resistance and you know the temperature difference, inside temperature is T1, outside temperature is T2. So it's like knowing potential difference and resistance, you can tell the current. Okay. So these are of JE level, JE advanced, I can say. But let's solve this problem. So for this blue layer that we have considered, we have to find out the thermal resistance. What is the formula for thermal resistance? L by Ka. Length through which heat has to pass divided by conductivity and area of cross section. Okay. Now we have already visualized the heat flow here. It is flowing from inside to outside. As heat flows this way through this blue layer, there is a small distance that it has to pass through. Okay. So what we are going to do is we are going to assume the radius of this blue layer as small r. Okay, from layer to layer, that radius keeps changing. Innermost layer has the radius a, outermost layer has the radius b. Okay, there are many layers like this. Okay, so let's say this innermost layer's radius is r, and the thickness of this layer is dr. Okay, now some of you may be used to this, for some of you this may be new. Dr means change in the radius. Okay, d stands for change or small variation. Okay. So as you go from one layer to the next layer, radius will change, no? So from one layer to next layer, the change in radius is dr. That becomes the thickness of the layer. That's all. Okay. Now what we want is the thermal resistance of this layer. Let's write an expression for it. Thermal resistance basic formula is L by Ka. L is the length through which heat has to pass. K is conductivity. A is area of cross section through which it has to pass. So the small thermal resistance of this spherical layer becomes L, the distance by which heat has to pass is dr. Okay. As heat crosses this blue layer, the distance it travels is dr divided by conductivity is K. Every layer has the same conductivity. If they want to make the question even more difficult, they can even give you conductivity varying from radius to radius. Okay. For now, we have assumed conductivity to be same everywhere. So K. Next, as heat passes through this spherical layer, the area that it crosses is the area of the sphere itself. Okay. And how do you write area of sphere? 4 pi r square. That blue sphere has a radius small r. So its area will be 4 pi r square, and heat has to pass through that area from inside to outside. So that's the area of cross section. So this is the expression for thermal resistance of that spherical element layer. Okay, hope this is clear. If you have any doubt anywhere, you can unmute and ask. Now we need the total thermal resistance of the entire object that is given to us. And since these layers are placed one after another, heat has to pass through these layers one by one. The layers are in series. So series means how do you find out effective resistance? Summation of individual resistances. So you'll have to sum up all the DRs. Summing up DRs means integrating DRs. Therefore, total thermal resistance becomes integral of dr divided by K into 4 pi r square. And the limits for integration, you want to cover all the spherical layers, no? So you'll have to take the radius of the first spherical layer and the radius of the last spherical layer as the limits. Radius of the first spherical layer is A, and the last spherical layer through which heat passes, the radius is B. So limits for R will be from A to B. That's all. This will give us the total thermal resistance. So let me write it here. Integral A to B. Length was dr, conductivity was K, area of cross section is 4 pi r square. Okay. So 1 by 4 pi k, these are constants, you can put them outside the integration. And 1 by r square dr can be written as r power minus 2 dr. And we have to substitute limits a to b. We'll first integrate and then substitute limits. One of you tell me the basic formula for integration first. What is integral x power n dx? Provided n is not equal to minus 1. What is the answer to this?
X power n plus 1 by n plus 1.
Good. X power n plus 1 divided by n plus 1. Now here we have integral r power minus 2 dr. So in place of x we have r. In place of n we have minus 2. So minus 2 plus 1 divided by minus 2 plus 1. Minus 2 plus 1 is minus 1. So you get a minus sign and r power minus 1. So the integral is minus 1 by r. So the thermal resistance now becomes 1 by 4 pi k. Integral is minus 1 by r. And now we substitute limits a to b. Okay. We'll substitute the upper limit first. You can put the minus outside, or yeah, we'll put the minus outside. Minus 1 by 4 pi k multiplied with 1 by b minus 1 by a. Okay. Now you send the minus inside. Then it becomes 1 by 4 pi k into 1 by a minus 1 by b. So this is the total thermal resistance. And what we wanted is the heat current, rate of heat flow. Current is potential difference divided by resistance. So heat current will be temperature difference divided by resistance. Temperature difference, you know, T1 minus T2. Thermal resistance, you have derived. Divide them, you'll get the current. Okay. But understand what made this a difficult or tricky problem to solve. We didn't know the cross-sectional area through which, uh, the cross-sectional area through which heat flows was not uniform. That was the problem here. Heat was flowing from inside to outside like this. So what we had to do is we had to visualize heat crossing layers one by one. So for one layer, we wrote the resistance and then we integrated to find out the total resistance. Okay. Let's see if you can do that for this cone. Okay. Uh, I'll give you some ideas also how to solve. Just a moment. Let me draw the diagram properly. Okay. This is to help you with the visualization. Suppose there's a cone like this and we cut out some part of it near the vertex of the cone. If you cut out some part of it near the vertex of the cone, let's say this part has been cut out. You can still visualize the complete cone, but that part doesn't exist now. Okay. This remaining part of the cone is called the frustrum. Okay, just remember this name. Those of you who study mathematics, you should be knowing this anyway. I think you have problems like in geometry where you will be asked to find out the volume of the frustrum of the cone and such things. Okay. So let me give you the dimensions. Assume the radius here is R1 or okay, let's take A and B only. Let's say the radius here is A. Radius means from here to here. Okay, this is A. This radius is B. Okay, or shall I make it slightly easier for you? Okay, instead of A and B, take them as R and 3R. Okay, and you need to know the distance also, this length. Let's say the length from here to here is given to you as L. Okay, so length of the frustrum itself is L, not the complete cone. Fine. Conductivity is also given to you. Let the conductivity be K. Uniform conductivity. and one end of the frustrum is maintained at a temperature, let's say T1. The other end is maintained at temperature T2. Okay. Anyway, temperatures and all will apply in the last step only. No, heat current is equal to temperature difference divided by resistance. The main thing is to find out the thermal resistance here. Okay. So forget about temperatures. Conductivity and dimensions have been given to you. You have to find out the thermal resistance when heat flows from left side to right side. Okay. Think about this, all of you. I'll give you some time. Come up with an idea. How are you going to write equations? Okay, I don't want the exact equation, but what will you treat this as a collection of? How will you find out the thermal resistance of each part of that collection? Okay. Those ideas are what I want. Okay, think about it. Any idea, any of you? How can this problem be solved? Okay. The first thing to do is imagine heat flow. Assume left end of the cone is at higher temperature, right end is at lower temperature. Heat will be flowing from left to right. Next thing to do is visualize the cross sections or the layers through which heat has to pass. Okay. One such layer can be imagined like this. Just a moment. Some thickness will be there, definitely. It has to pass through thick layers. Yeah. So it's kind of like this. As the heat flows from left side to right side, it has to pass through disks. Okay. One after another. Okay. So this is one such disk. Now the disk shown here, I'm trying to show you this thing in 3 dimensions, but in 2D, if you visualize, like exactly from the side, if you see, looks somewhat like this. Just a moment. Okay. If you see it from the side, it looks like this. And we have to cut out the frustum and all. Okay. These questions involve a lot of mathematics, but basic mathematics only. You will be able to do it. Okay. So situation is like this. Heat flows from left to right, let's assume. Okay. As heat flows from left to right, it has to pass the disks one by one. And the disk has some thickness. Okay. Let's say the thickness of the disk. Okay. What to name the thickness and all also is actually an idea itself. Okay. You need to know how to name the thickness. And as heat flows through this disk, the cross section is in the shape of a circle that we had visualized before also. It has to flow through circular disks like this. So if you want to write the area of cross section, you need to know the radius of this disk R, okay, which keeps changing from disk to disk as the heat flows from left to right. The first disk which the heat passes through has a radius of cross section R. Okay. The last disk that it passes through has radius 3R. So that radius is a variable. So this random disk that we have considered in between, let's say its radius is small r. Okay. Assume its thickness. Now you can't call its thickness as dr. Why? Because dr has a meaning. Dr means change in radius or the variation in radius. Okay. Now radius is in the y direction according to this diagram. Okay. Vertical line y direction. Thickness is in the x direction. So when you go from one disk to the next disk, thickness is not equal to the variation or the change in radius. Okay. For spheres, it was. Okay. As heat flows from the inner sphere to the outer sphere, the distance by which heat flows itself is the distance by which the radius changes. Okay. But here it's not like this. Suppose heat flow was in this direction, then the small distance by which heat flows can be equated to the small change in radius. But heat is not flowing upwards, no, heat is flowing sideways. So here you cannot write distance of heat flow as dr. So that will be another variable. Okay. So since it's flowing in the x direction, you can call it as dx if you want. Okay. That's the distance by which heat flows when it passes through one disk. And there are many disks like that placed one after another. So the idea now is to express the thermal resistance of one disk. Since it's a thin disk, it will have a small thermal resistance. Okay. Let us use the symbol R for resistance only. For radius, I will use the symbol A. Let's say this radius is A and the last radius is 3A. Okay, just to avoid confusion. Capital R stands for resistance. A and small r, they stand for radius. Okay. So this disk, which has a slight thickness, will have some thermal resistance. And as heat has to flow from one disk to the next one and so on, it's like all the disks are placed in series. So how do you find out total thermal resistance? Integrate or sum up all the small resistances. And since they are DRs, you sum them up by integrating. That is the idea. So now the first thing to do is write the thermal resistance of one disk. If you can do that, then you can integrate and find the total thermal resistance. Then you can tell heat current also. How to write thermal resistance of one disk? Thermal resistance basic formula is L by Ka. Okay. The distance by which heat flows, that is L. K is conductivity, A is the area of cross section. Now, as heat flows through this disk, the distance by which heat flows is dx. Okay, when it goes from one side of the disk to the other side, the small distance it covers is dx. Conductivity K is uniform anyway. All the disks have the same conductivity. Next, area of cross section through which the heat flows is the area of the disk, which is disk is in the form of a circle. So the area becomes pi r square. Therefore, the thermal resistance of the disk becomes L divided by Ka. But there is a problem in this. Okay, 4 pi r square. What is the problem? If you want to find out total thermal resistance, you'll have to integrate this. So you'll have to integrate dx by k into 4 pi. Okay, wait, why did I take 4 pi r square? Area is pi r square only, no? Yeah, k into pi r square. The problem here is mathematically again. You are integrating with respect to x, but from one disk to another disk. Okay, like in this case, you can visualize from one disk to another disk, the radius is variable. This disk has one radius, this disk has a different radius. Okay, small r is a variable. So if small r is the variable, then integration will have to be in terms of dr, not in terms of dx. Okay, you can't say integral x power n dr is x power n plus 1 by n plus 1. That is wrong. Okay, integral x power n dx is x power n plus 1 by n plus 1. So variable in terms of which the function is written and the variable with respect to which you are integrating should be the same. That is the trouble here, okay, in this problem. So how to overcome this problem? You will have to express thickness and the radius in terms of the same variable. And here you get more, you'll have to involve more mathematics. Okay. How? You'll have to write both of them in terms of one variable. For that, this original diagram will be helpful. Okay, like imagining the full cone will be helpful, full triangle. Let me show you how. Just a moment, I'll copy paste this. So we have to express thickness and radius in terms of the same variable. Okay. Consider this as the x-axis. So when you look at it from the side, it looks like a triangle. The cone looks like a triangle. Okay. Now consider a random layer somewhere here. That layer will have some thickness as well, dx. Okay. Now the distance from this point to this point, you can call this as x. Okay. I am assuming this is the origin. And horizontal, I'm taking x-axis, vertical, I'm taking y-axis. This distance you can call as x. And then the radius can be called as y. Okay. We need a relation between x and y. How do we relate x and y? We can use the equation of this straight line. Okay. Generally, how do you write equation of straight line passing through origin? Y is equal to mx. Okay. This you will learn in mathematics. Some of you might have already learned also. This is how you write the equation of straight line passing through the origin. Okay. Now, y is the radius of the disk. It keeps varying from disk to disk. X is the distance of the disk that also keeps varying, but slope will be constant for a straight line. Y and x will change based on the point, but slope will be constant. How to find out slope of a straight line? Y2 minus y1 by x2 minus x1. For that, you will have to use the original diagram. Okay. In the original diagram, the last y coordinate is 3a. You can treat that as y2. The first y coordinate is a. You can treat that as y1. So y2, y1 are known to us. Next, x2, x1. We don't know the distance of the last part of the cone. We don't know the distance of the first part of the frustrum. But x2 minus x1 will be equal to L. That we can say. Okay. This last x coordinate is x2. This first x coordinate is x1. We don't know those values separately, but x2 minus x1 is the length of the frustrum. So y2 is 3a, y1 is a. So y2 minus y1 becomes 3a minus a, that is 2a. And x2 minus x1 is L. Dividing these two gives us the slope. So slope here is 2a by L. Lot of geometry is involved in this problem. Okay. Therefore, we can say that y is equal to 2a by L into x. Okay. Still, why are we doing all this? Y is the radius of the disk. X is the distance of the disk. Okay. So we are now able to express radius in terms of distance x. Okay. Then you can say that dr, okay, if r is equal to 2a by L into x, then dr can be written as 2a by L. 2a by L is constant multiplied with dx. So we'll be able to express dx in terms of dr, L by 2a into dr. Why do we have to do this? Because, as I said, you will need to express dx in terms of dr to be able to integrate this. That is why we are doing all this. So how did we get dx? Dx is L by 2a into dr. That we will write here now. So 1 by k pi, that constant is there anyway. Integral. In place of dx now, you will write L dr divided by 2a. Okay, lot of mathematics as I said. Divided by r square is anyway there. Okay. Now it is, I mean, from here onwards, it is slightly easy. L is constant, 2a is constant, k pi is already there. Integral 1 by r square dr again becomes minus 1 by r. And limits for radius will be from a to 3a. If you substitute that, you will get the thermal resistance of one disk. Okay, wait, not one disk. Total frustrum. You'll get the thermal resistance. And then you can find out rate of heat flow also. So this is how you find out the effective rate of heat transfer through a frustrum from one end to the other end. You'll have to, I mean, the general approach is this. You have to first visualize from where to where heat is going, whether it's that sphere question or this frustum question. If you visualize heat flow, in sphere it was radially outward. Okay. In frustrum, it is going from one side to the other side. So in sphere, when the heat flow is radially outward, the cross sections become spherical layers. Heat has to flow layer by layer. Okay. In this case, in case of frustrum, as heat flows from one side to the other side, the layers by which it passes become disks. Okay. It has to pass through disks one by one. Okay. So one layer's thermal resistance we'll find out first. In that process, a lot of mathematics will be involved, writing the thermal resistance of one layer. Then you integrate the thermal resistance of all layers, you get the total thermal resistance. Then you can tell net rate of heat flow also if you want. Okay, fine. I think this much is enough about conduction, thermal conduction. We have discussed in quite a lot of detail. So next class we'll be talking about convection. Convection, you don't have any formula in your syllabus. You just have to know what is the process of convection. And after that, we will discuss radiation, thermal radiation. That is very important. So we'll discuss all that in tomorrow's class. Okay. Thank you all. We'll continue tomorrow.